let's look at graph topologies. So the first slide is, it says don't use this function, and that is true. So the background here is that graph topologies have existed in MPI since MPI 1 days, but the function that was provided in MPI 1 has a problem which has been fixed by the new functions in MPI 3. So the one that was in MPI 1 we discourage you to use. The problem is that this function required every process to specify the entire communication graph of all processes at each process. So you're specifying, suppose you're running on a million process system, you would be specifying a graph of all these million processes communicating on each of those each process, which is a memory problem. It consumes you'll have to pass very large arrays to specify all that information, and you don't have that much memory on big systems. So that problem has been fixed. So this function avoid the original graph create function avoid. There is a new interface in MPI 3 that allows you to specify this information more scalable way, that is in a distributed way. You don't need to specify the whole graph everywhere. You can each process can specify its own information, and the MPI implementation figures out. So there are two ways of passing that information. One is called the MPI distgraphcreate adjacent. So it takes a lot of parameters, but that's why there's a lot of detail. But in this method, each process has to specify its communication information with its nearest neighbor. So let's say you have the communication graph, who's communicating with whom and how much. Each of those processes has to specify its communication graph with its nearest neighbors. That is, who are the sources and the destinations. That is, whom is it receiving from, and whom is it communicating to. And optionally, you can pass a weight along weight information for that edge of the graph. What does the weight mean? So weight is just it's implementation defined. The MPI doesn't say what is the meaning of the weight, but it could be some measure of how much the communication is. So one could be the number of messages, or it could be the size of the message, the amount of data that is communicated. So in general, the idea here is the higher the number means more the communication is happening. If you don't want to pass a weight, you can just pass unweighted. There is an option. So in this case, this function is called on each process. You pass the old communicator, and then you pass. These are just arrays of sources. Who is communicating with you, who is sending data to you. So this is the in degree is the size of these arrays. So this is the list of who are communicating with you, and these are the weights of that graph edge if you wish to provide a weight. So some of the details you can see in the MPI standard, because there is a bit of detail here, which you probably don't need to worry about until you actually use it. And similarly, the out degree is whom are you communicating with, whom are you sending to, how many, that is, how many target ranks are you communicating with, and these are the list of those ranks and the associated weights again. Info is, it's the info object, the same thing that was in one-sided communication. You can pass some more hints to the MPI implementation. That's some detail that you could look up. This is whether to reorder the communicator or not. And the output of this is another communicator that has this graph topology associated with it. And if you had given the reorder as 1, the implementation may have done a reordering, so now you have the new ranks. One potential drawback of this method is that each edge in the graph is specified twice. Once as an out edge and once as an in edge. So a process is saying I'm sending to that process. That process is also saying I'm receiving from this process. So it's doubly conveying the same information twice, which in the other method, which I'm going to get to, you don't need to do that. So this is just an example of how you would fill in all the various parameters in this. So suppose this was the communication graph. You had 6 processes, and this was how they were communicating. Then process 0 would pass these parameters. 0 has nobody sending to rank 0, so its in degree is 0, and then the other parameters are not relevant. Once this is 0, the sources and source weights gets ignored, so those are not relevant. The out degree is 2. It is communicating with 2 of them, and the destination ranks are 3 and 1. The order doesn't matter. You could say 1 and 3 or 3 and 1. So that would be passed to the function on the previous page. The weights we have not. This is an unweighted graph. There is no weight on any of the edges, so we are not passing any weight. We can pass MPI unweighted. There is a constant defined. Similarly, for rank 1, this has an in degree of 3. There are 3 sending data to it, and an out degree of 2. There are 2 ranks it is sending data to, and the sources are 0. Where is that? 4, 0, and 2. So 4, 0, and 2 are the ones sending to it, and 3 and 4 are the ones it is sending to. So it's that kind of detail that goes into this function. So this is, each process will be calling this function with this kind of parameter list. Okay, is that clear? So that was this graph create adjacent, and it's called adjacent because you pass this adjacency information, your nearest neighbor. The other way is called MPI distgraphcreate. It's the most general way, and in some sense the most powerful. In this method, each process doesn't need to specify its connectivity information. Any process can specify any other process's connectivity information as long as the whole graph is somehow conveyed. So there is no duplicate that there is a destination and a source that the double conveying the same thing twice. That doesn't happen here. So you could one rank could pass half the graph information for the whole thing. Another could pass the other half of the whole graph, and that's done. So this is most powerful. It is also more difficult for the MPI implementation because it's being passed in a way that it is a little harder to understand. I won't go through the details of how this function is called, but you can look it up when you need to use it. So this example, you can see how the same one is being passed in the other option of the distgraphcreate function. Then there are some query functions available. That is MPI distgraph neighbors count. So the calling process, how many neighbors does it have? Both sending data to it and the ones it is sending data to. So you can query that, and then you get the number of the in degree and the out degree. And this is just gives the number of processes. If you want the actual list of processes, so this is effectively you're querying the graph. Who are the neighbors I'm communicating with? Then you can use this function. So that's similar to all the query functions associated with the Cartesian topology. You can find out who your neighbors are and so forth. And finally, given a communicator, you can find out whether there is a topology associated with it. If you are writing a library, the user passes you a communicator, you don't know whether there is a topology or not. So this function you can call Topo test. So it will return MPI graph. This is the old MPI graph, so ignore, this is not to be, should avoid using that one. Then is it a Cartesian, is it a distributed graph, or is it undefined? That means there is no topology. So if you just give it MPI com world with no topology, to this function, you'll get MPI undefined as the return, as the status out here. So that's how libraries can decipher whether there is something on the communicator. Any questions so far? So this was, how to use this. We have some more information about, some data about, some results that Bill will talk about. But anything so far?
Okay. So I wanted to give you a little more data on where we stand with dealing with the topologies and the impact of the topologies, and some of the consequences of having multiple cores and multiple chips per node. So the systems have gotten to be quite complex. And maybe the short form of this is I'm not going to give you good news. I wish I could. And in fact, a lot of what Rajeev has talked about was intended to enable the implementers of MPI to give you some relief from dealing with these issues. Unfortunately, we're just not very far along there yet. So it has taken, in many cases, it's taken the vendors a long time to admit that topology is important. The problem here is that, yes, dealing with topology is complex. It adds a fair amount of burden to a programmer who's going after the biggest performance. So rather than admit that life is not fair and not always fun, a lot of vendors have decided to pretend that life is fun and say everything is fine, don't worry about it. And the reality is that it's not that good, and you do have to worry about this, and you can see that in some of these results. So, for example, this plot here just shows some distribution of nodes that were allocated on our machine, Blue Waters. Until recently, the scheduler that allocated the resources took advantage of the fact that, of course, the topology was unimportant because the network was so good that it didn't really matter. And so it allocated nodes. This is a big torus. So it allocated, a couple nodes over here and some over here, and there's little gaps and whatnot where there are nodes in the middle, because of course it wasn't going to make any difference. We finally convinced them that we could prove that it made a difference, and we're now running a scheduler that doesn't do stuff like this, and most codes are significantly faster. But that has also come with other costs that the scheduling framework itself is sluggish and slow. So what do we do? Well, I'll give you some information on thinking about this, and it will, in some ways, the biggest problem has been trying to take advantage of some of the things that Pete talked about yesterday. Yes?
Sorry, when you say the scheduler doesn't do this, what does the scheduler do if it has a very full machine and with several holes and it?
So so the trade-off there is I can take a job and I can distribute it through the holes, and then the downside of that is that application may run more slowly if it's communication sensitive, and the applications that are running between the pieces may suddenly run more slowly because they're now sharing that network. Or you can just wait until an appropriate space opens up. So it's a very challenging problem given a selection of requests that come in at various times to pack those into the available topology to get good performance. It's made more complex by the fact that the communication that you have is not necessarily restricted to your volume of the machine. So two things can happen to add communication from elsewhere to that. So the first thing is, if for some reason you need to do I/O, that data has to flow over some network. It's often, in our case, it is the same network. It's a fast network, okay? So that means that communication will flow wherever it needs to reach the nodes that are connected to the I/O system. The other thing that happens is the networks tend to be built to operate independent of any sort of partitioning for individual jobs. What this means is that if a node on the network becomes really busy and needs to redirect traffic, it will just redirect it. And it might redirect it out of your part of the domain. And so you can be a very well-behaved application and suddenly be pounded by I/O data or by redirected traffic. And this is a long problem. There was a machine called, Paul remembers, the Intel Delta. I knew someone who was running on it who was doing some benchmarking, and all of a sudden times were terrible. And what was happening was the I/O system was on this side of the machine, and the tapes were on this side of the machine, and a backup started. And just filled up the network with I/O traffic. And his job was right in the middle. And this is a very hard problem to solve because it's expensive to put in a separate network for the I/O. That's not really a solution, right? And in fact, if you do that, then people will say, well, why didn't you spend that money on the network for me, right? So it's not that people don't know what they're doing. It's that these are very challenging problems and a very challenging set of trade-offs. And so what we have to learn to do is deal with it. So in some ways, what Pete was talking about last night is really the solution. So one of the reasons why this becomes a real problem is because you've done a partitioning of the work that is supposed to give equal work to the different processes and nodes. And as I'll show, the network traffic can create some of those performance irregularities. It's another source, but it's really one of many of these performance irregularities. And so if the code is a little more flexible for performance irregularities, the impact of the topology, the placement can be reduced. Another way to think about this is, again, we talked about applications are very common for an application to do communication and computation. Well, that means that the network is idle a lot of the time. If instead you can organize things so that you're using the network over a greater span of time, but your requirements on its performance are a little more lenient, then you may have better overall performance. You know, a lot of what's been done in these networks has been trying to make the burst performance for those bulk synchronous applications work reasonably well. But again, that's very challenging because the performance requirements are very high. And I'll show some graphs about that. Okay, so in fact, this is pretty much what I've said here is that with the performance irregularities coming from all sorts of places, the assumption that you have a load balanced code because you divided the work up evenly is no longer a good assumption. It in fact has not been a good assumption for some time, but we've been able to live with it. And it's going to be harder and harder to live with it because there are more and more sources of these performance irregularities. Okay. So one example, so here again is a simple mesh. And the thing to remember is communication doesn't happen in isolation. So here we have one case where this process is communicating with that one. Why is it doing that? Well, one reason might be that the virtual and physical placement is not what you think. That happens. Or it may simply be that you've got a more complex communication pattern in an unstructured mesh or something, and it's close by but not an immediate neighbor. And then we have another process sending up here. And the problem is right there where you have two of these messages over the same link. And so if they're all running as fast as they can, you suddenly have a place where you have half the effective bandwidth for each of those messages. And so if your mental model of what's going on is messages flow at a certain rate, as they're going over that link, like we saw this morning, they're suddenly going to be half as fast. And that's a big gap, a big change in your performance. And particularly if you have codes that are communication phase and computation, you only have to have one of these. Because then everybody else will end up waiting for the people who are slow, right? So in fact, one of the challenges with doing the topology mapping is trying to figure out what is the function you're trying to optimize. Okay? And part of the problem is that the function you really want to optimize is to minimize overall solution time for the code. And the next sort of stand-in for that particularly if it's a bulk synchronous sort of code, would be to minimize the communication time. Well, minimizing the communication time means looking for the maximum of effects like this and minimizing those. So it's not average length. It's not even maximum length of message. It's like the maximum overlap of messages in time. And this is a very hard thing to optimize. And so nobody does this yet. Okay. And this is a pretty simple pattern. You could easily have 3, 4, 5, 6, 7 communication patterns crossing over the same link. Again, if you can make things more loosely synchronous so that you're not as bound up in the quick completion of the communication, that gives you more flexibility. You can tolerate more of this. So here are some examples trying to understand how well you might be able to do a halo exchange. And one of the things to get out of this is I did these because doing a ping pong test, so ping pong, 2 processes send data back and forth, and you measure the time, and you get a communication rate, maybe you get a latency. Then you take that and you use it in your complexity models. How many people have done that? Right. Gee, okay. Well, maybe that's good. Because for modern systems, as we'll see, those measurements no longer are necessarily very helpful. There was a time when that was a reasonable thing to do, but that time is long past. So what was going on here is I did some measurements where instead of looking at the sort of artificial pattern, I said, well, why don't I just measure a halo exchange? And I'll remove all the other stuff out of it. So for example, this is sort of a mock halo exchange. There's no vector gathers and scatters. It only moves contiguous data. So I don't have any effects from the fact that some data might not be contiguous around. I just want to look at how quickly can I move data to a bunch of neighbors and do it in different ways. And you can see some of the things that we talked about this morning. So for example, do the I receives and then do those individual sends. On the BGQ with 8 of them, I would got a rate of 660 or 711 megabytes per second. But if I did I sends as well as I receives, I got performance that was basically twice as high. Okay, so that's why you should definitely do that. The effect on the Cray is essentially no effect performance with it. But also I found these numbers are really kind of small, particularly compared to this. So I've tried to understand that, and it's taken me a while. And in fact, I have brand new slides for you. So one thing I did was, well, what if it's contention? What if there's something going on? So what I can do instead is I can say, well, I'm going to take essentially the stencil. I'm going to take some process somewhere, and I'm going to have it send to its neighbors, and I'm going to have those neighbors receive, but I'm going to have everybody else stay quiet. And so then what performance do I get? Well, on the BGQ, I get this number, about 3 gigabytes per second. And on the Cray, I get this number, 5.5 gigabytes per second. Ooh, that's cool. That's a nice number. But if I look at that, and here's a larger set of numbers. So 4 neighbors, periodic, this is non-periodic, this is periodic, and a sequence of machines. And then I ask, what is the ratio between doing them with one sender and the corresponding receivers versus the full halo exchange where all processes are sending and all processes are receiving? What you get is this. So the blue genes run about a ratio of 2, which you can sort of think about. It kind of makes sense. I'm in the full exchange, I'm both sending and receiving. Maybe that takes twice as long. But the Cray has these numbers, they keep getting worse. As the machine this is an old machine, a not so old machine. This is a just replaced machine. So that just looks wrong. So what is that? Well, it turns out that there are two effects for this. And one of them is, in fact, here, and we'll show that. And the effect comes from two places. So one comes from the mapping of processes onto the physical topology. Ooh, let's see where I've got them. Part of the problem, I mentioned this at the beginning, part of the problem is we've got these SMP nodes, and they've got multiple cores. We used to call those processors before Intel redefined processor. And we typically put an MPI process on each of those cores, and we let them communicate. So if you look at papers that talk about complexity models for message passing programs, there is a sort of abstract machine model, which is I've got a processor, which is a core, which is running an MPI process, and it's connected to a network, and it's talking to another MPI process, which is on a core that's somewhere else. And then I talk about the latency between those and the bandwidth between those and so forth. That used to be what the machines looked like a long time ago. It's not what they look like today. So here's two quite simplified examples of what they look like. So the BGQ node, you've got the processor chip and effectively integrated networks that are talking out along different links in the different mesh directions. The Cray is a little more complicated. It has multi-chip nodes that talk to, in pairs, talk to a network interface that then itself is inserted into a mesh and can send data in different directions along the mesh, X, Y, and Z, once the data gets there. Okay, so one system, we've got multiple paths into the network. In the Cray, we have multiple paths in the network, but we only have single paths to the nodes. And in both cases, if all of the cores in a node are sending, they can try to push data out faster than the various links can manage it. So wrote another little test that uses some non-standard routines to find out about the physical topology. So it discovers processes that are on the same node and processes that are on the same other node, maybe in the same same direction and say one hop away. And it does ping pong communication, but using one core, then two cores, then three cores until they're in both of these machines until there are 16 cores communicating between the same two nodes. Okay. And then we look at the data. Now, the things the hardware can do. So some of the numbers have to be looked at with a little bit of a grain of salt. But what you get are things like this. So this is a number of integers. It's a log scale. And this is the aggregate communication rate. This process is sending, here is sending 10. This is two processes sending 10, three processes sending 10, and so forth. And this is, let's see, here, this is a gigabyte per second right here. So see this nice aggregate, and this is about the right spread. So as you add more processes, you get more communication performance. And then it starts to flatten out, and it gets squeezed together. And what that means, another way to look at it, is the rate per process. Okay. So down here for short messages, the rate per process is basically constant, regardless of how many cores are sending. But as we get out to larger messages, The highest rate per process is when there's only one process sending. As soon as I have more processes sending, the rate per process goes down to the point where if I have 16 processes, I've lost almost an order of magnitude. So if I'm doing very synchronous, I'm in my communication phase and I'm forcing all of my processes to communicate, and they all have to go along that link, then I'm going to be a factor of 10 slower. It's going to take much longer to move the data. Now, for the Cray, this is a real problem because it's got a couple of single paths into the system. We don't see this as much on BlueGene because for a halo exchange, I'm typically sending out among the different links, and it doesn't have the same sort of single point of contention inside the system. But if you're sending the same direction, you still get the same sort of behavior. And this is low. The Cray was up here, so the peak performance on the BlueGene is lower. And in this case, it's also sort of smoother. It keeps going up and then whack. It's a nice fast transition. And again, the rate per MPI process, sort of this, all 16 curves are right in here. There's almost identical performance until you get to a few hundred ints, and then it just fans out. And again, this is one process sending, this is 16 processes sending. The reason for this test, the reason you see that is because they're all sending along that same link to a neighboring node. Okay, so thing to realize right now with these multi-core chips is your MPI processes can overwhelm your network. So if you do a ping pong test and then figure out how fast things should be, that's going to give you the wrong data because that ping pong test won't give you this information. So if all of the processes are sending and they're sending along too few links, you'll end up with them all being slower than you expect, and you'll get the same sort of loss of scalability that we saw this morning. You have contention over the links, meaning that processes are waiting for the resource to be available. In this morning's case, the resource was getting data into the node. Here, the resource is the message link, the wire, or the fiber, whatever, between 2 points in the system. Okay. Now, does communication overlap help? So typical to write these code, even if we use the non-blocking operations, it's typical that you do MPI I receives, MPI I sends, then wait all. What you can do instead is I receives, I sends, compute, and then wait all. So you start the communication, you compute. Of course, you have to be careful to compute only with the data that's available. Then you do the wait all, and you have to do some cleanup. That makes the computation stage phases more complex, and for a number of reasons may also impact the performance. So can it help? Well, maybe. So this is for a particular communication pattern. This is on the BlueGene, and so this is the ratio of the time doing communication then computation divided by the time doing the overlap communication and computation. So at 1, you have done no harm. Higher than 1, you've accomplished something that you're getting communication computation overlap. Less than 1, your attempt at overlapping communication and computation is slowing things down. So this is sort of interesting because 1 is here. And so for this test on the BlueGene, you had to be out at about 10,000 ints worth of data before you started to pick up a benefit from doing the communication computation overlap, which I found bizarre. Okay, so I need to look into this some more. This seems unusual. But once you're past that, it does quite well. Right? So this is 1, 2, 3, 4, up to 16 processes. So the more processes I added, the more benefit that I got from the overlap, just like I would hope. The Cray gave both a happier and sadder picture. So the happier part is doing the overlap almost never caused harm. And so this is sort of one. I get a significant benefit, actually fairly large, as long as I don't go to really large messages where the benefit disappears again. And we can even look at how much of the communication is overlapped in this case. So this is the fraction of the communication time that is not overlapped on the Cray. And so again, if you have at least, I don't know what it's like, 4, maybe 6 MPI processes communicating, then you get a reasonably good fraction. So this is like 0.6 is overlapped. This is, you're all the way down here. This is all but 0.2 is overlapped. You can get a significant amount of communication computation overlap, but only if you're moving a lot of data. So that's where it sits right now. Now, one of the things that I'm going to keep looking at is, particularly on the Cray, using the RMA with, there's a sort of experimental implementation of RMA that's quite fast, which should provide a lot of this overlap in hardware so that the impact on the other running applications shouldn't be as severe. Okay. Yeah.
My first question you have just answered, but the second question is, how much is because of resource contention? How much is this because MPI is eating cycles?
So I don't know the answer to that. I expect that a significant amount of this is due to the fact that MPI is eating cycles in managing the communication flow, which is why I would hope that the RMA would do better. There have been a lot of research papers that have looked at exactly the issue of the communication computation overlap, the cost of that, and have shown that in the cases where you can take advantage of the network RDMA capabilities, you get very good performance. A lot of those papers have tended to emphasize the large messages, though, which is out here, which is where things are doing pretty well anyway. So there's been less work looking over here, which is where I think you're interested, and certainly I'm also interested in that. I think this will get better over time, again, but the message here is that the SMPs, you can't think of them as isolated cores running all by themselves without influencing each other. And so another reason to put this up is tomorrow we're going to start talking about programming the chips using, say, OpenMP or doing hybrid model programming. This is a reason why you might want to do that rather than MPI everywhere. So running an MPI process on every core has lots of advantages. It gives you a very nice way to enforce locality. It makes you make sure you've got locality. But one of the things that you might be missing is that by having all of those MPI processes communicating independently, you may not be getting the full effective use of the cores because they're going to be sharing that resource. Whereas if you did something more dynamic or more heterogeneous, where you had a few cores communicating, other cores doing the computation, and appropriately dynamically sharing the work with low overhead, which is a huge caveat, but can also be done, you might be able to get much better performance than the numbers for the Cray in particular for the achieved performance for the Halo exchange are really pretty terrible. And I expect that to become more common rather than less common. Okay. Okay, any questions on that? Yes.
On the x-axis, the ints, is that the function of some compute work, or is that like just some test?
So the what I did here, you've got a whole bunch of parameters. So what I did was I did an update to a work array of this size and sent 1/10 of this amount of data. Right? So this data is meant to be suggestive. Your mileage will definitely vary. What I wanted to understand was just how much potential there might be for getting the communication computation overlap and where we'd see these sorts of effects. So I think the feeling I'm getting from this is it can be there, but you have to be careful, and that depending on communication computation overlap, but still having a fairly tight requirement is probably going to be a hard way to get the best performance. But it is a it is a potential improvement. After all, here, let's see. Here, which is not an unreasonable size, that's about 2,000 word communication, 20,000 word data. You're covering about 50% of the communication with the computation. That's not a bad place to be.